Yes. Hey. Welcome back. Today, let's solve the problem. Merge case sorted linked lists. Yeah. And there is a very similar problem called merge case sorted arrays. And if we have done that, then this is just a complete replication of that. But the only difference is that we are using linked lists instead of arrays. So what the question tells us is that we are given an array of sorted linked lists of different sizes, and our task is to merge them in such a way that after merging the lists, they will be stored in a single list, and the list will also be sorted. So, for example, if we consider this example, we have linked list of 1, 2, and 3, 4 and 5, 5 and 6, and 7 and 8. So, what will happen? First, you have to merge them, and on top of merging, it has to be in sorted order. So what will be the output? Will be 1, 2, 3, 4, 5, 5, 6, 7, and 8. So how might you do that? There are actually two ways to do this. So what one of the things you can do is to actually take all the elements of of the linked list and put it into a single linked list. And now first let's go with the complete naive solution, and that is to actually take all the elements of the linked list, put it inside an array, and then sort the array, and then create a linked list out of it. And this is like a pure brute force. And so, what will be the time complexity? First, you have to traverse through the entire linked list to put it inside an array. So that will be n times m. Where it is theoretically not n times m, because actually the number of what do you call elements present in the array multiplied by the length of each list, and then you have to sort it. So it will be for simplicity, we will call that entire thing as n, like the number of elements present times the length of each list. So let's call that as n. So it will be n log n with n extra space. Technically, it's 2n because first we will create an array, and using the array, we will create what you call the new linked list. And so, what is the another implementation? We will have a linked list with no values, and for each value in the linked list, like each value in the array, we'll just compare the first value of each of the linked lists, and then we will appropriately put that element which is smallest on top of the head or the dummy node which you have taken, and that will be extremely complicated. Like the time complexity of that is very high. So what we can do is that actually we can use a heap where we will put all the nodes in the heap, like the head of all the linked lists. And what we will do, we will pop out each node, like each head node, which is like we'll pop out each head, and we'll just compare the values with the top of the yeah. There's no need for to do any comparison also, mainly because heap has the property of we'll use min heap, so the naturally the elements will be sorted. And then what we can do is that we can directly append the topmost element of the heap to our linked list, to our new list, and then we can return the list. So first, let's go with the pure brute force solution. So we'll have ARR, and okay, the array is already called ARR, so we'll call that as okay. We'll call it res, and for uh, linked list in ARR. So yeah, we'll call it head because each element in the ARR is actually a head of the linked list. So cur is equal to head, and we don't even actually need to mention the reference to the current head also. So what we can do, while head exists, yeah, it's data over here. So we'll put reservoir data, and let's just return return node with value none, and let's just print out our res one. Yeah, always debug your code like whatever you're doing. And yeah, we actually have our array over here. And since the actual array is already sorted 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, we actually got a sorted array early, but we should not forget to do the rest dot sort, and then we will have dummy. This is a very popular way of creating linked list. And at the end, what we'll do, we'll return dummy dot next. And what we'll do, we'll have a reference to a current pointer, and for data in our result, we'll create a new node. It's nothing but the node with the value of data. And what we'll do cur.next. So we'll have the current pointer pointing to head. So we have cur with value none, and the cur is pointing over here. How can I? Yeah, cur is pointing over here, and we have a new node. So what we have to do? We have to take cur over here, and we have to take cur next, and we have to point it to new node. So we'll do cur.next is equal to new node. And after this, what you have to do? You have to take this cur, and now what happened is that a link has been formed over here. So now what we have to do? We have to take the cur from here and move it over here. So what we'll do? Cur is cur.next. Let me just remove this thing. And then we are returning dummy.next, and this should theoretically work. Let's just check it out. And yeah, let's just commit it out. I don't know if it will TLA or something. I don't think it will TLA, but still. Okay, yeah, it works. Yeah, this is one way to do it. This is the pure naive implementation where we are actually putting it inside a result array. So this will actually take space of n, and then we have one more thing which will take space of n. So it will be nothing but 2n. So let's try to optimize it. So what we'll do? First of all, we will import queue. I mean heap. What we'll do again? Let's just write the linked list again. 1, 2, and 3, 4 and 5, 5 and 6, 7, 7 and 8. So what we'll do? We'll put the head of every node in the head of every linked list in the heap. So this everything will be every entire thing will be in the actual heap now. And so what will happen? So and since it is a heap, the sorted order will be maintained. So it will actually be like this only. So we'll pop out the top of the heap. So this is the top of the heap. So we'll have a dummy over here, and dummy. So what we'll do? We'll just create the connection to one, and then again we'll pop from the heap. Let's take a better example. Let's just switch it around. 4, 2, 8, 5. Yeah. So now what we'll do? After that, the heap will shift itself, and this will go over here, and this will go over here, and so the 2 will be removed. So a new connection to 2 will be done, and 5 is there, and it will again get shifted down, and then a 4 will be removed, and 4 will be connected, and yeah. One blunder which I made was that the actual lists are already sorted, so I can't actually change it like that. I can't do 4, 3. Let's change the relative order of entering. Yeah. Let's imagine that our this one linked list itself was given like this. So rather than 1, 2, 3, 4, 5, 5, 6, 7, 8, it was 1, 2, 3, 5, 6, 7, 8, 4, 5, or like that. So what will happen? Naturally, this will be shifted up like this. So next pointer two will be done, and the 2 will be removed. So again it will be shifted, and again next pointer to 3 will be done, and 3 will also be removed, and again next pointer to 4, and on. So it will continue, and at the end you can just remove return dummy.next to get the actual result. So we'll just have a heap, and we'll have dummy, and we'll have a current pointer pointing to dummy. So what we'll do for every head in array, for every head in ARR, so what we'll do, uh, into the heap, we'll push the head. But if you know one thing, so how does heap do the comparison? It will do the comparison by comparing the actual data which is present. So if we put 1, 2, 3, 4, 5, it can actually compare that. But when you pass linked list, so it can't compare that. So what we have to do is that we have to have a custom, what you call a custom class, which will actually have some properties like less than and greater than implementation, so that heap can actually sort the values. So let's just have a, since this is a node, we will wrap our node in a custom node. Yeah, we have to do this. We'll have self and the data, and self dot data is actually equal to data, and self dot next is actually equal to none. And so what we will do, and then we'll have less than, which will do nothing but it will take in will have the self pointer also, but it will actually take in the node value to be compared. And what it will do, it will return self dot data, which is the current data, current node which is being compared to the node which is to be actually compared, which is self to the actual node which is combine that data. And we'll have the what you call equals to also. We'll have self comma data, and you'll return the self dot data is actually the data is actually equal to the, it's not data here, it is node, and will be equal to node dot data. So what we'll do, into the heap we'll push in our custom node now with the value of head dot data. And in the beginning I tried to do like this, but what will happen is that your reference to the next pointer will be lost. So you're just pushing the head dot data, right? So what will happen? This is not the only value which is present in the head. If you do head dot next, then you will actually have a pointer to, you'll actually have a pointer pointing to your you'll have actually have a pointer pointing to the next node, and that reference will be lost when you do just head dot data. So what we'll do, we'll have a self dot a reference pointer also, like a reference also, like reference to the current node, and we'll do self dot reference is equal to node. I hope you understood why I did this, because if you just push in the head dot data, the reference to the next pointer will be lost, and we don't want that. We absolutely don't want that. So we'll just pass in the head dot data and the actual head also. Yeah. So now what has happened? We have created our custom node, and we have not lost our pointer data also. And currently I'm keeping the next as none. If you want, we can actually have the reference as the next itself, but let's not go for that route now. Yeah. So now what has happened is that all the data has been pushed into a heap. So now while heap exists, not head. So what we will do, the node which we will get, which is actually the head, is actually from the heap. So you pop the current, yeah. Now you pop the current head which has the lowest value from the heap. So now what you have to do, just think once. So you have the reference to current over here. So you have to do the same thing. And since this is our custom node, and the custom next is actually none, so there's no need for us to check for anything. So we can directly link it. So what we will do, we have curve, and curve dot next will be actually pointing to our head dot data. So what we'll do, we'll just wrap it back in the node object, because I think in the driver code they actually don't use custom data and all. Yeah, they're just printing node dot data, so this might not be required. We'll just check it out because even I have not checked that out. And so what you will do now? Now you'll move your curve, and now what you have to do? So you have to check if the next node is not null, and you can't do like head dot next over here, because head dot next is always null. So what you have to do? You have to get the reference to the head, and that's what we did by passing the actual head pointer also. So head dot reference actually has the data, actually has the pointer pointing to the next node. So what you'll do, head dot ref dot next will actually give you the pointer pointing to the next node. And if this is this only if this exists, so what you'll do, heap period into the heap, you will push the it is heap again. You will push the custom node again with the value head dot ref dot next dot data and head dot ref dot next. Yeah, and yeah, now you can directly return dummy dot next, and let's just compile and run it once. And yeah, it's working. I'll just submit it. Yeah, this also runs. So I have not actually tried this. What will happen if I just do this? If I do compile and run, will it work? It should also theoretically work. Okay, head dot data is actually pointing to the integer value. It is actually pointing to the data, not the node. Yeah, this also works. There's no need to actually wrap it in the custom node, mainly because we are also calling it data itself. And even in their definition of node also it's called data. So there's no need for us to do any changes. But if we call this something like, if you call it as val or something, then you will obviously, you can't like send in your custom node. You have to change it accordingly. And yeah, that's all for it. Thank you for watching and goodbye.